Welcome everyone. I'm excited to start this training module with you today. This is the basic knowledge of Honeywell DCS C300 Training Module 01. I'm Deepak Gorai, Deputy Manager of C&I at Singareni Thermal Power Plant, and I've meticulously crafted this course to give you a fresh and insightful perspective. Over the course of this presentation, we'll cover essential topics such as the architecture, modules, and I/O configurations of the Honeywell DCS C300, how it integrates into industrial automation, and what you need to know as operators, engineers, or maintenance personnel. Let's get started and explore this exciting subject together. Let's talk about DCS, or Distributed Control System. Essentially, it's a control system where control functions are spread out across multiple controllers, rather than being all centralized in one single unit. Instead of having just one main controller, you have several controllers, often called nodes, placed near the actual field devices like sensors and actuators. These controllers are interconnected through a high-speed communication network, which links them to operator stations, HMIs, and engineering stations. This setup allows for real-time monitoring, control, and automation of industrial processes, ensuring everything runs smoothly and efficiently. Now let's look at the key components of a DCS. First, you have the controllers themselves. They perform control algorithms such as PID, logic, and sequences to manage the process. Then, there are the I/O modules, which serve as the interface to the field devices, connecting sensors and actuators to the controllers. Next, there are the operator stations, or HMIs. These are your dashboards for monitoring the process, receiving alarms, and sometimes manually intervening if needed. The engineering station is where configuration, logic programming, and maintenance happen, giving engineers the tools they need to keep the system running optimally. Additionally, there's the historian or database, which stores trends, events, and process data, crucial for analysis and reporting. And finally, the communication network ties everything together, ensuring seamless data flow between controllers, operator stations, and engineering stations. Overall, a DCS provides a flexible, reliable way to monitor, control, and automate complex industrial processes, making it a vital part of modern automation systems. Let's take a closer look at some of the key reasons why distributed control systems, or DCS, are widely used across industries. First, distributed control means that multiple controllers manage local processes, which helps reduce reliance on a single central controller and enhances overall system stability. Reliability and redundancy are also crucial. Many DCS systems, like Honeywell C300, include backup controllers, networks, and power supplies. This setup minimizes downtime and ensures continuous operation, even if one component fails. Real-time control is another vital aspect. DCS continuously monitors the process and provides deterministic responses, which is essential for managing critical processes safely and efficiently. Scalability is a big advantage too. As plants grow, you can easily expand the system by adding more controllers and I/O points without needing to redesign everything from scratch. That flexibility makes DCS suitable for large and complex facilities. Integration capabilities are also impressive. DCS can seamlessly connect with SCADA systems, historians, alarm management, safety systems, and various field devices, creating a comprehensive control environment. Supporting advanced control strategies is another reason for its popularity. DCS handles complex control algorithms like PID loops, batch and sequence control, and even advanced process control techniques, which optimize plant performance. Centralized monitoring allows operators to oversee and control the entire plant from human-machine interfaces or operator stations, making plant management more efficient. Data recording is equally important. Historian databases store trends, events, and alarms, which helps with analysis, reporting, and meeting regulatory requirements. Safety and security are also integrated into DCS. They can include safety interlocks, cybersecurity features, and alarm management to protect both personnel and equipment. All these features combined explain why industries rely on DCS. It offers a reliable, scalable, and automated approach to process control, ensuring safe and efficient operations across various sectors. Now, let's take a closer look at some of the common industrial applications where control systems play a crucial role. First, in power plants, control systems are essential for managing boiler operations, turbine control, and feedwater systems. These components need precise regulation to ensure efficient and safe power generation. Next, in petrochemical and refinery operations, continuous chemical processes, distillation, and blending require accurate control to maintain product quality and safety standards. Then, in pharmaceuticals and food production, batch processing and recipe management are key. Control systems help ensure consistency and compliance with strict regulations. Moving on to water and wastewater treatment, control systems oversee pumping, filtration, and chemical dosing, everything necessary to produce clean water and treat waste effectively. Finally, in the oil and gas industry, pipeline monitoring, pumping stations, and offshore rigs all depend heavily on reliable control systems to operate safely and efficiently. Overall, these applications highlight how control systems are integral to a wide range of industries, helping optimize processes, improve safety, and ensure product quality across the board. Now, let's take a closer look at the various use cases for the Honeywell C300 DCS. In power plants, it's used for turbine control, boiler control, and feedwater systems, ensuring smooth and reliable operation. Moving to the chemical and refinery sectors, it handles continuous process control, safety interlocks, and product quality control, which are critical for maintaining safety and efficiency. In the petrochemical, oil, and gas industries, the C300 supports large-scale distributed automation, process optimization, and hazardous area integration, helping manage complex and potentially dangerous environments safely. When it comes to critical infrastructure, high availability and reliability are non-negotiable, and the C300 delivers just that, ensuring essential systems stay operational at all times. Now, on to scalability and flexibility, one of the key strengths of this system. It supports everything from small plants to very large distributed facilities. Multiple C300 controllers can be networked together, handling thousands of I/O points, which means it can grow along with your operations. Plus, it's versatile enough to integrate with both Control Hive, which offers virtualized controllers, and legacy I/O systems, making transitions and expansions smoother. Let's talk about advanced control capabilities. With Control Builder, you get a comprehensive set of tools like function block diagrams, sequential function charts, and the ability to develop custom algorithms and PID loops. This allows for precise control, whether you're managing APC, batch processes, or complex sequences. In fact, the C300 often outperforms many competitors in continuous, batch, and hybrid process control. So, why do industries often choose the Honeywell C300 DCS over other systems? It's because it combines robust scalability, advanced control features, and proven reliability, making it a trusted choice for critical and complex applications across various industries. Let's take a closer look at seamless integration. Our solution is fully integrated with Experian PKS, meaning you get a unified platform that combines SCADA and HMI through Experian Station, PhD Historian for trends, reports, and alarms, and safety systems via Safety Manager. This level of integration is smoother than some other DCS vendors that often require third-party software to connect these components. This seamless approach reduces complexity and improves reliability. Moving on, our proven track record speaks volumes. Our systems are widely used across power plants, oil and gas facilities, chemical and petrochemical industries, and critical infrastructure worldwide. Decades of deployment have built trust in our solutions, especially regarding reliability and lifecycle support. Now, when it comes to engineering and maintenance efficiency, we've made things straightforward. Tools like Control Builder and I/O import wizards help streamline configuration tasks. Plus, templates and migration utilities make upgrades and expansions much simpler, saving both time and effort. Diagnostics and advanced alarms are designed to reduce troubleshooting time, ensuring your operations stay smooth. Finally, cybersecurity and compliance are top priorities. Our modern PKS systems, like R500+, come with built-in cybersecurity features such as secure network protocols, role-based access controls, and data integrity checks. These features help protect your critical infrastructure. We also ensure compliance with industry standards like NERC and IEC 62443, which is essential for maintaining security and reliability in critical environments. Altogether, this integrated, proven, efficient, and secure approach helps ensure your operations are reliable, scalable, and protected against evolving cyber threats. Today, I want to give you an overview of the Honeywell DCS C300. The official name of this controller is the C300 controller. It is an integral part of the Honeywell Experian Process Knowledge System, or PKS, which is designed to provide a comprehensive control and information system for industrial processes. The DCS C300 is classified as a distributed control system, or DCS controller, meaning it distributes control tasks across multiple modules to ensure reliability and efficiency. Its primary purpose is to handle process automation, control, and monitoring in large industrial plants. These plants can include power generation facilities, chemical manufacturing, refining operations, petrochemical complexes, and more. Essentially, the DCS C300 plays a crucial role in managing complex, large-scale industrial processes, ensuring they run smoothly, safely, and efficiently. As we move forward in this presentation, keep in mind how this system forms the backbone of many critical industrial operations, enabling precise control and real-time monitoring. Now, let's take a closer look at the I/O link in the C300 CPU. This feature is a crucial part of modern automation systems, as it enables seamless communication between the controller and connected devices. By integrating I/O link directly into the C300 CPU, we achieve a more streamlined and flexible setup. This means easier configuration, better diagnostics, and improved data exchange with sensors and actuators. Overall, the inclusion of I/O link enhances our system's efficiency and scalability, making it a vital component for advanced automation solutions. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at what a chassis is and why it's so important. Essentially, a chassis is a physical rack or frame that holds all the I/O modules in the system. Think of it as the backbone that keeps everything organized and accessible. Each slot within the chassis can host different types of modules, whether that's a controller, an I/O module, or an interface module. Now, when it comes to the C300 DCS, there are two main series of chassis to be aware of. The Series A chassis is the older model, and it supports limited capacity with its modules. On the other hand, the Series C chassis is the newer version, designed to support higher I/O capacity and faster scan rates, which is crucial for more demanding applications. The chassis itself provides several key functions. First, it offers physical mounting for all the modules, ensuring everything stays securely in place. It also handles power distribution, so all modules get the power they need to operate reliably. And importantly, it includes a data backplane, which facilitates communication between modules, making sure data flows smoothly across the system. Focusing on the Series A chassis, it has specific capacity limits. For instance, you can connect up to 83 Series A I/O chassis through an FTEB per C300 system. And within each Series A chassis, you can fit a maximum of 16 I/O units per FTEB. These numbers are essential to understand, as they help us plan the system's scalability and ensure we're designing within the supported limits. FTEB, or Field Terminal Expansion Bus, is essentially a bus connection that links multiple remote I/O chassis directly to the main C300 controller. This setup allows the controller to access remote I/O modules without the need for physical proximity or being in the same rack, which offers a lot of flexibility in system design. Each FTEB can support multiple modules and remote chassis, but of course, this is subject to the overall capacity limits of the C300 system. This makes it scalable depending on your specific application needs. Typical uses for FTEB include extending I/O to field locations that are far from the controller, which can be a real game changer in large or complex plant layouts. It also helps reduce wiring complexity by bringing the field wiring to a nearby chassis, simplifying installation and maintenance. When we talk about capacity, the maximum number of Series A/I/O chassis that can be connected through FTEB per C300 is 83. That's quite substantial and allows for extensive I/O expansion. Each Series A/I/O chassis, or FTEB, can support up to 16 I/O units. In addition, the C300 can support up to 3 serial interface modules, 12 DeviceNet modules, and 10 SSD Profibus modules. These capacities ensure that the system can handle various communication protocols and interface requirements efficiently. Overall, the FTEB is a vital component for building scalable, flexible, and efficient control systems, especially when dealing with remote field locations or large-scale installations. It helps us optimize wiring, reduce costs, and improve overall system accessibility. Let's take a closer look at the controller module, which is essentially the CPU of the system. It acts as the main processor, executing control strategies and managing communication with various I/O modules. An important feature to note is that redundancy is supported here, ensuring reliability and continuous operation. Moving on to the analog input modules, these are responsible for receiving continuous signals such as 420 mA, 010V, RTDs, and thermocouples. Some versions also support heart diagnostics, which adds diagnostic capabilities and enhances troubleshooting. The analog output modules, on the other hand, send analog signals to field devices like valves and actuators. And just like the input modules, some analog output modules are available with heart functionality for better communication and diagnostics. Now, for digital signals, we have the digital input modules, which handle discrete on-off signals from switches or status contacts. These are vital for simple binary data collection. Complementing that are the digital output modules, which control devices such as relays, solenoids, or alarms with on-off commands. They essentially turn devices on or off based on control logic. Next, there are the pulse, counter, and frequency modules. These are important for measuring pulses, event counts, and frequencies. Think of flow pulses or RPM measurements. They provide real-time data critical for process monitoring. Communication and interface modules provide connectivity to various protocols like HART, Profibus, and Foundation Fieldbus. They ensure seamless communication between the controller and field devices or other systems. The IOTA, or I/O termination assembly, along with extender modules, serve to terminate field wiring, connect I/O modules to the backplane, and extend I/O capacity when needed. They help organize and expand the system efficiently. Finally, the power supply modules are essential for powering the entire chassis and modules. They can be configured for redundancy or non-redundant setups, depending on the reliability requirements. All these modules together form the backbone of the Honeywell C300 system, enabling flexible, reliable, and scalable control solutions for complex industrial processes. Let's take a closer look at the I/O types and their key selection parameters. Starting with AI, or analog input modules, the main factors to consider include the signal type, such as 420 mA, 010V, RTD, or thermocouple. Accuracy and resolution are critical to ensure precise measurements. Input isolation, whether single-ended or differential, affects noise immunity and wiring complexity. Support for heart and diagnostics can provide valuable device health information. Additionally, input filtering and response time are important for signal stability and system responsiveness. Some modules include built-in heart modem for easier diagnostics and configuration. Moving on to AO, or analog output modules, key parameters include the output range, like 420 mA or 010 V, and drive capability, which involves compliance voltage and current load. Resolution and linearity are vital for accurate control signals. Support for heart and diagnostics can help monitor loop health and troubleshoot issues. Similar to AI modules, redundancy support depends on the application, and proper wiring and I/O link rules must be followed to ensure reliability. For DI, or digital inputs, the main considerations are voltage type, such as 24 VDC or 120 VAC, and whether the module supports common ground or isolated inputs. Input filtering and debounce are necessary to prevent false triggers. Channel count can be quite high, often supporting 32 channels per module, especially for 24 VDC inputs. Some modules can handle AC voltage or higher voltage ranges, adding flexibility. Redundancy is also possible here, depending on the system design. When it comes to DO, or digital outputs, important factors include the output type, whether relay, transistor, SSR, or triac, and the load drive capacity, meaning the current and voltage it can switch safely. Protective features like flyback diodes or fuses help safeguard the system. Response speed is crucial, especially for control applications. These modules typically support 32 channels or more, and for high current or AC loads, relay extensions may be necessary. As with other I/O types, redundancy support can be incorporated as needed, but always ensure the module can handle fault situations. In summary, when selecting I/O modules, it's essential to match their electrical and functional specifications to your system requirements. Carefully consider the application context, signal types, and system architecture to ensure reliable, accurate, and safe operation across your entire control system. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the C300 I/O capacity table, which compares the specifications for 50 millisecond and 20 millisecond cycle times. First, when it comes to the maximum number of I/O units per C300, for the 50 MSCEE, the options are 1, 2, or 4 units, with a maximum of 64 units if you see Note 4. In contrast, the 20 MSCEE supports up to 80 units, but only if you're using PM IOPs or Series C IOMs. Moving on, the maximum number of I/O units per C300 I/O link is 40 for the 50 ms configuration, and it increases to 64 for the 20 ms setup, which makes sense given the higher speed requirements. Now, focusing on Series A I/O related components, these are not supported in the 20 ms CEE setup, but for the 50 ms, you can connect up to 83 Series A I/O chassis through the FTEB per C300. Each Series A I/O chassis supports up to 16 I/O units per FTEB, which is important for scalability. Regarding serial interfaces, the C300 can support up to 3 serial interface modules, but only for the 50 ms configuration. Each FTEB can host 1 serial interface module. Similarly, for DeviceNet modules, the maximum per C300 is 12, and per FTEB it's 4. The SSD Profibus modules follow the same pattern, with 10 per C300 and 4 per FTEB. Finally, for FFFIM4 related modules, these are not supported in the 20 ms setup. In the 50 ms system, you can have up to 15 redundant or non-redundant FIM4s per C3001, and for FIM8s, the maximum is 8. For PGM2 related modules, again, not supported in the 20 ms cycle, but in the 50 ms setup, you could have up to 4 redundant or non-redundant PGM2 modules per C3001. Overall, this table highlights how the system's capacity scales with the cycle time and shows the flexibility and limitations you need to consider when designing your control architecture. In this slide, I want to walk you through the key Honeywell Series 8 C300 modules and accessories listed in our table. First, we have the controller and infrastructure components, including the S8 C300 controller Yoda, which is coded and comes in black, with the part number 8C-TCNTA1. This forms the core of the system. Next, the RAM charger module, part number 51,454,475-100, is essential for power management, along with a 30-inch cable, 51,202,330-300, that connects the battery RAM charger. For redundancy and reliability, we also include a redundant controller cable, part number 51,305,988-36. Moving into the input and output modules, we have two types of headers. The two HB16S8 header board, also coded and part number 8C-SHEDA1. These are crucial for connecting various communication and signal modules. For analog inputs, we have the S8 AI non-HART IOM, which supports 16 channels and is coded, with part number 8C-PAINA1. Complementing that, we have the high-level AI, the S8 HLAI Yoda, also 16 channels, coded with part number 8C-TAIXA1. Notice that these modules are designed for high reliability and coded for environmental protection. Similarly, for analog outputs, we have the S8 AO non-HART IOM, supporting 16 channels, coded with part number 8C-PAONA1, and the Yoda version, also 16 channels, coded with part number 8C-TAOXA1. These outputs are vital for controlling external devices. The digital input modules include the S8DI24V IOM with 32 channels, coded, part number 8C-PDILA1, and its Yoda version for redundancy, part number 8C-TDILA1. For digital outputs, the S8DO24V IOM supports 32 channels, coded with part number 8C-PDODA1, and the Yoda version, part number 8C-TDODA1. We also have measurement modules like the S8RTD IOM, supporting 16 channels, coded part number 8C-PAIMA1, and the corresponding Yoda module, 8C-TAIMA1. Importantly, the same part number applies to the thermocouple modules, the S8TC IOM and Yoda, both supporting 16 channels and coded, which simplifies inventory and maintenance. Overall, these modules and accessories form a comprehensive, robust system designed for high performance and environmental resilience, aligning with our overall goal of reliable automation and control in demanding industrial settings. Let's take a closer look at the wiring overview for this digital input module. First, the input voltage range is between 18 and 30 volts DC, which is typical for industrial sensors and control signals. The input current is quite low, ranging from 2 to 10 milliamps, ensuring minimal power consumption. The device recognizes two logic levels, 0 volts for a low signal and 24 volts for a high signal, which aligns with standard industrial control logic. To ensure clean signals and avoid false triggers, there's an input filtering of about 2 milliseconds, which helps smooth out any noise or brief glitches. Speaking of noise, this module provides noise suppression greater than 60 decibels at 60 Hz, which is crucial in noisy industrial environments. Its response time is very fast, less than 1 millisecond, allowing for quick detection of input changes. The operating temperature range spans from -40 to 85 degrees Celsius, so it can operate reliably in extreme conditions. Humidity tolerance is also broad, from 0 to 95%, non-condensing, making it suitable for various environments. The protection rating is NEMA4IP66, meaning it's well protected against dust, water, and other environmental factors, ideal for harsh settings. Finally, the module itself is the Honeywell 8C-PDILA1, a 24-volt DC digital input module designed specifically for the Experian Series 8 C300 controller. It features 32 channels and provides galvanic isolation, which is vital for ensuring reliable and safe operation in industrial environments by preventing electrical faults from propagating across the system. Connecting all these points, This wiring overview emphasizes durability, reliability, and precision, key themes when designing robust industrial control systems. Let's take a closer look at the wiring overview for this digital output module. First, it has 32 output channels, which means it can control a variety of external devices simultaneously. The output type is sourced, so it provides a positive voltage to the load. It operates at a voltage rating of 24 VDC, ensuring compatibility with many industrial devices. The module itself can supply a current of up to 105 milliamps per channel, which is typically enough for controlling relays, solenoids, or actuators. The load voltage can go up to 30 VDC, giving some flexibility for different applications. Field isolation is included, which is critical for protecting the system from electrical noise and potential faults in the external devices. Additionally, this module features a coated version, providing enhanced protection in harsh environments. Think of dust, moisture, or corrosive conditions. This specific digital output module, the Honeywell 8C PDODA1, is designed for the Experian Series 8 system. Its main role is to control external devices reliably and safely, making it a key component in automation and control systems. By understanding these wiring details, we can ensure proper installation and optimal performance in our applications. Now, let's take a closer look at the 8C PAINA1 analog input module, specifically focusing on its wiring basics. This module offers 16 single-ended analog input channels, which means each channel measures a single signal relative to ground. These channels are versatile because they can accept different input types, either 4 to 20 milliamps or 1 to 5 volts DC, and you can configure each channel according to your specific needs. The module is designed to plug directly into the IOTA wiring system, simplifying field wiring connections and ensuring a secure, reliable connection. When it comes to isolation, the channels are grouped, usually 8 channels per isolation group, which helps prevent interference between signals and enhances measurement accuracy. Power-wise, the module requires an external 24 VDC supply, especially when you're using loop-powered transmitters. This power feeds the transmitters and ensures they operate correctly within your control system. Overall, the Honeywell 8C PAINA1 is a high-quality, robust module built for industrial environments. It's designed for high performance, with features like hot-swappable operation and built-in self-diagnostics that support continuous process control. It's also fully compatible with Honeywell's modular IOTA architecture, providing the precision and reliability needed for demanding automation applications. Now, let's take a closer look at the Honeywell 8C PAONA1, which is an analog output module specifically designed for industrial automation systems. This module provides 16 channels of 4 to 20 milliampere current output, making it ideal for controlling actuators and recording devices across various applications. One of the key advantages here is its flexibility. It can operate either with internal or external field power, depending on how you configure the I/O terminal adapter, or IOTA. This adaptability ensures it can fit into different system setups seamlessly. Moving on to the wiring overview, the module's output type is a 4 to 20 milliamp current signal, which is standard for industrial control because it's less susceptible to noise over long distances. With 16 output channels, you can control multiple devices from a single module, streamlining your system design. The load resistance that the module can support ranges from 50 to 800 ohms, provided you're using a 22 to 28 volt DC power supply. This range gives you some flexibility depending on your load requirements. The module is rated for a 24 volt DC power supply, aligning with common industrial standards. Its current rating is 190 milliamps, which is sufficient for most typical control applications. An important safety feature is its configurable safe state behavior, meaning you can set each channel to either hold the last value or shed to a safe value in case of a fault or loss of communication. This enhances the reliability and safety of your system. Additionally, the module includes open wire detection, which is crucial for identifying wiring issues. When an open wire is detected, it can trigger a soft failure indication for the specific channel, allowing for quick troubleshooting and minimizing downtime. Overall, the Honeywell 8C-PAONA1 offers a robust and flexible solution for analog output needs in industrial environments, linking your control system to field devices efficiently and safely. Let's now take a closer look at the Experian Engineering Studio. This platform acts as the overall engineering environment for the Experian PKS system. It's where we manage and configure the entire control and visualization setup. One of its key functions is handling SCADA and HMI displays through the Experian station, allowing operators to visualize processes effectively. It also lets us configure alarms, trends, and historian points via the PhD tool, which is essential for tracking and analyzing process data over time. Another important aspect is that Experian Engineering Studio enables importing or migrating projects from older PKS versions, ensuring smooth upgrades and continuity. It also integrates seamlessly with Control Builder, which links control logic directly to operator displays, creating a cohesive system. Now, moving on to Control Builder, this is our primary tool for programming and configuring the C300 controller. It's where we create control logic using various programming methods like function block diagrams, sequential function charts, or custom algorithms and PID loops. Control Builder also allows us to configure I/O points and control modules, making sure our control strategies are precise and tailored to specific process needs. Additionally, it supports associating alarms and events with control points, which helps in proactive process management. Its modular design makes maintenance and future upgrades easier. Plus, it integrates with the I/O import wizard, enabling bulk creation of points, which saves time when setting up complex systems. Overall, whether we're working on continuous, batch, or hybrid processes, Control Builder is where all control strategies come to life. It's the backbone of our control logic development, ensuring everything runs smoothly and efficiently. Let's take a closer look at Control Hive, which is particularly relevant for newer PKS R500 systems. Essentially, it's a virtualized control execution environment designed specifically for the C300 logic. What this means is that it allows logic to run independently of the physical controller hardware, providing greater flexibility. It also supports redundant and scalable control execution, so you can ensure reliability and grow your system as needed. Control Hive works seamlessly with Control Builder, making logic deployment more straightforward. You'll find it especially useful in large, modular, or virtualized control system architectures where flexibility and scalability are key. Moving on to migration utilities, these tools are essential when you're upgrading projects between different PKS versions, like from R400 to R500. Their main role is to convert old Control Builder projects into formats compatible with the new PKS version. They also handle upgrading SCADA displays, historian points, alarms, and control logic, ensuring everything works smoothly with the latest C300 features. And then there's the I/O import wizard, which helps automate and accelerate the creation of points for the C300. It allows for bulk creation of analog, digital, calculated, and derived points, saving a lot of manual effort. It also maps physical I/O modules to logical points, applies templates for alarm limits, scaling, and engineering units, and validates I/O addresses, types, and conflicts. This tool reduces manual configuration errors and speeds up large plant projects, making the entire process more efficient and reliable. Now, let's move on to the installation procedure for the Experian PKS R500 and HS410. In this section, I'll walk you through the key steps involved in setting up these critical components. First, it's important to ensure that all hardware is correctly positioned and secured according to the manufacturer's guidelines. Proper installation not only guarantees optimal performance, but also ensures safety and reliability. Next, we need to connect the modules following the specific wiring diagrams provided in the manuals, making sure all connections are tight and properly insulated. This step is crucial to prevent any communication issues down the line. After wiring, the configuration process begins, where we set up the system parameters to match our operational requirements. This involves using the appropriate software tools to configure network settings, communication protocols, and safety parameters. Lastly, I want to emphasize the importance of thorough testing after installation. Running diagnostics and verifying system responses will help us identify and address any issues early on. Remember, a well-executed installation sets the foundation for a smooth and efficient operation of the Experian PKS and HS410 systems, which aligns perfectly with our overall goal of achieving reliable automation infrastructure. Let's take a closer look at the I/O Import Wizard overview. This is a powerful tool within Experian Engineering Studio and Control Builder that helps simplify and automate the process of configuring points and I/O channels for C300 controllers or control hive systems. One of its primary functions is automatic point creation. Instead of manually setting up each point, the wizard generates process points, whether analog, digital, calculated, or derived, based on your field I/O definitions. This saves a lot of time and reduces errors, especially when dealing with large numbers of I/O points. Another key feature is I/O device mapping. This maps the physical I/O modules and channels directly to the logical points within the DCS, supporting various module types like analog input and output, digital input and output, RTDs, thermocouples, and more. The wizard also uses predefined templates for configuration. These templates set default properties such as engineering units, scaling, alarm limits, display properties, and security permissions. This ensures consistency across your points and simplifies the setup process. Bulk operations are another important aspect. You can import hundreds or thousands of points at once from sources like CSV or Excel sheets, third-party PLC configurations, or existing DCS projects. This is especially useful for system migrations or large-scale updates. To ensure everything is accurate, the wizard performs validation checks. It verifies that all points are consistent with the controller's configuration, checking for I/O channel availability, type compatibility, whether analog or digital, and address conflicts. Finally, integration is seamless. Imported points are automatically recognized by Control Builder for logic association, and they are also integrated with PhD Historian for trend analysis and alarm or event collection. Overall, the I/O Import Wizard is designed to streamline your setup process, improve accuracy, and ensure smooth integration within the overall control system architecture. Let's walk through the basic C300 logic creation workflow within the Configuration Studio. First, you need to create a system hierarchy. Think of it like setting the foundation. You start by creating an asset or a parent asset where all your controller logic and I/O will reside. This helps organize your project effectively. Next, you'll add the C300 controller itself, along with its associated I/O modules, into this hierarchy. This step ensures that your hardware is properly represented in the project. Once your hardware is set up, you'll launch the Control Builder application. This is where the logical development begins. In the Control Builder, you'll create a control module, or CM. These modules are like containers. They organize your function block diagrams and define the control strategy for specific equipment, such as a motor or a valve. Now, to build your control logic, you'll use function blocks. These are the building blocks of your control scheme. You simply drag them from the library and wire them together, creating the desired control logic. What's great about these blocks is that they are reusable and come with predefined features for parameters, alarms, and algorithms, making your development process more efficient. The next step is to assign I/O points. You connect your function blocks to the physical input and output points that you've configured for the C300. This links your software logic directly to the hardware signals. Finally, you'll download and publish your logic. This means loading the control strategy from the Configuration Studio into the C300 controller, activating your control scheme so it can operate in real time. This workflow, creating a hierarchy, adding hardware, developing logic with function blocks, linking I/O, and then deploying, is fundamental to implementing reliable and efficient control systems with the C300.